Hello, everybody. Welcome to today's TPR live session. Today's session is titled, Is it linear? What does that mean? Well, the goal of this presentation is to teach you a concept, the concept of linearity, that isn't always taught this way in high school, and to show you how you can use it to avoid some common math mistakes, and also to tie some different concepts together. Let's start by doing some examples. So if you could grab a piece of paper and a pencil, and for each of the following 12 questions, mark whether the expression or the equation is true or false. Does the right-hand side appropriately represent the left-hand side, or has there been a mistake made? So true or false for each of these 12. Get out a pencil, mark it down. I'll give you guys a minute to work on this yourselves. And then we'll circle back to this at the end of today's session. So take a minute or two. And if you haven't seen some of these yet, like the last two have some calculus, don't worry about it. Just do the ones that you're familiar with. Okay, no worries if you weren't totally finished. Hopefully you got through a good number of those. Before we dive into linearity, let's talk about function notation. This just means the conventions around how functions are written. So first of all, what is a function? Take a second to, I might have just given you a preview of what I'm going to say, but take a second to put into your own words what a function is. So what is a function? Think about that for a second. What is a function? How would you define it? Yeah, so question about, yeah, don't worry if you haven't seen calculus yet. That's just one of the things we're tying together. We're not going to really talk about that during the presentation, so don't worry about it. Yeah, that's mostly for seniors in high school, depending, maybe freshmen in college, something like that. This will mostly be focused on Algebra 1, Algebra 2 type content. Good question. So what is a function? One way we could define that is that it relates inputs to outputs. Okay, so here's a visual way that I could draw this. So in blue, we have our various inputs, so maybe numbers like 1, 2, 3, 4. And then we have our function, which is this rule, which tells us how the inputs get mapped or related to the outputs. So for example, if we start with 1, our function, this black arrow tells us that the output is b. So we could say that f of 1 equals b. We could say that f of 2 equals a. Okay, and here's how we would write that in function notation. All right, you've probably seen some things like this in algebra. F of x equals x squared. Okay, what this is saying is that the blue part, the argument of the function, this is the input. So we're putting in x. The thing we're getting out is x squared. That's written over here. And f is just telling us what's the name of our function. And let me give you another visual representation of this for those of you who are more visual learners. We can think of the function as this machine, which I've drawn as a black box here. So this big black box is like the function. It's taking some input, and it's giving you some output, and it's doing something in the middle. Okay, there's some rule that it applies to the input to give you the output. So let's see some examples. Let's say that, let's say we start with a function f of x equals 2x. what this means is that our function f takes the input, doubles it, and then gives you the output. So for example, if our input was, I don't know, 3, our function will take 3, double it, and give us 6, right? Or, oops, if instead of 3, we had, say, let's say we had x here, then if we take x, we double it, we get 2x. All right. And finally, I'll do just one more of these before moving on to another function as an example. Let's say that we started with a plus b. All right. Our function tells us we double whatever we put in. And so our output is 2a plus b. All right. So far, so good. Let's look at 2 more examples quickly. Let's say f of x equals x squared. In this case, if we were to say, right, if we put in 2, our function squares it, so we get 2 squared, which is 4. Or instead, if we put in x, we would square it and get x squared. Or what if I put in a plus b? Okay, so I put a plus b into our function. My function squares whatever I put in. And so what I get out, or I'll color code this too, is a plus b squared. Okay, and my function could be something more complicated. I won't go too crazy, but I don't know, let's just say that it's like 3x squared plus 2. Then whatever I put in, I apply that rule to it. So let's say that I were to plug in 5. Well, then I would do 3 times 5 squared plus 2. 5 squared is 25. 3 times 25 is 75. 75 plus 2 is 77. Great. So if I put in 5, this function gives me 77. Or let's say I put in a plus b. Then this function would give me as an output 3 times the quantity a plus b squared plus 2. All right. Perhaps I belabored that a little bit, but this tends to be a really tricky concept for many students, this idea of functional thinking and functional notation. So hopefully going through some examples like this helps clarify how this works. Yeah. The stuff we put in here is the argument. We apply some rule to it, and it gives us some output. And you can visualize it with these Dr. Seuss-like machines that I've drawn. Okay. So that's great. That's what functions are, and that's how we deal with function notation. What about linearity? Well, visually, a function is linear if its graph is a straight line. So we're familiar with functions like this from algebra class. The one on the right here, we're comfortable saying this looks pretty linear, or the one on the left, that is. And the one on the right here, we're comfortable visually saying that this one is not linear. Okay. So if the graph of a function curves, then that function isn't linear. Let's write down what the equations for these two functions are. For the one on the left, f of x is going to have the general form mx plus b, where m is the slope and b is the y-intercept. The one on the right is going to, in general, have the form f of x equals, and this actually isn't as important, the exact form of this for this presentation. would have the form x minus a squared plus b. The point is that one is linear, one is not. In particular, we said this was the slope, and this was the y-intercept, right? But the key point for this slide is just that these types of functions are linear on the left of the form y equals mx plus b, and on the right-hand side, anything else basically is not linear. And this parabola is just one example. All right. And hey, by the way, if you've joined me for previous sessions, welcome back. You probably know in that case that you should just jump in with questions anytime. You can just type your questions directly into the YouTube chat, and the wonderful Shadna will pass them along to me here, and then I'll be able to answer those questions. So feel free to ask as we go along. Okay, so now we'll define linearity, and then afterwards we're going to apply it to some examples. So we're going to take a closer look at this linear function. And let's consider two different values of this function. Oh yeah, how is this used in life? Yeah, great question. Yeah, this kind of thing will help you with math that you'll see on the SAT or ACT. You'll see more what I mean by that later on in the presentation in just a few minutes. And then also, yeah, this is like applicable in later life. I'm going to end with a slide about some of the future applications that you might see this on. But for now, it's about avoiding common math mistakes. Great question. You should always be thinking like, how is this useful? Right? Always be asking that. That's important. Let's consider two different points, A and B. So I can talk about the value of the function at this point A, and let me draw that for those of you who are more visual. Okay, I can say that the value that the function takes when x equals a, as drawn with these green dots, is called f of a. That's sort of what we were seeing on the previous slide. Similarly, I can look at the x value when x equals b, and I can find what value does the function have, where I just drew that bigger green dot. What value does the function have when x equals b? And we call that value f of b. Okay, so far so good. Now let's consider the value a plus b. So a was 3 tick marks away from the origin, 1, 2, 3. And it looks like b is 5 tick marks away from the origin. So a plus b would be 3 plus 5 is 8 tick marks away from the origin. Okay, so that means our value a plus b is out here. So let's think about a plus b. Okay, well, for a linear function, we have a special property. Okay, and let's see how that works in this particular example. So f of x here, what's the formula for this function f of x? Okay, the way that I've drawn it, it's 1/2 x. I can see that the slope is 1/2, since the rise divided by the run would be 1/2 in this case. So the function is f of x equals 1/2 x. So that means that f of a equals 1/2 of a. F of b would similarly be 1/2 b. Okay, f of a plus b, let's think about that. I haven't drawn that one yet. Okay, so I take the value a plus b, I go up to my function line, and I see what value the function has, which is represented on the y-axis, when x equals a plus b. All right. Okay, so when x equals a plus b, then I can still use the formula that I have, f of x equals 1/2 x, to say that f of a plus b is 1/2 of a plus b. But now notice that I can distribute the 1/2 across the a and the b. So this is the same as 1/2 a plus 1/2 b. But sort of the key insight here is that 1/2 a, this is just what we had for f of a, and 1/2 b is the same as what we had for f of b. So what we just found is that f of a plus b, in this case, equals f of a plus f of b. And this is what's called our linearity property. Okay, this is called linearity. Okay. So we can say a function is linear if f of a plus b equals f of a plus f of b. All right, and we can see an example of it with this straight line function. So now let's apply this to avoiding some common math mistakes. First, no, good question. We're not going to talk about any word problems today. Once we go through these next few examples, if you'd like to stick around a bit after the session to ask about word problems, we could talk a little more about that. But we're going to be talking mainly about different sorts of algebraic manipulations and how this concept will be useful in connecting them together and keeping them separated from each other also. So let's talk about this. 7 times quantity x plus 5. So you're maybe thinking to yourself, yes, I know, I can distribute the 7 over the x and the 5 since I know the distributive property. And I know that multiplication distributes over addition. Well, that's great, and that's all correct. Let's think of it in these function terms, though. All right, so what are we putting in? We can think about this like we're putting in the value x plus 5. All right, and we're applying to it this function that f of x equals 7x. So we're putting in x plus 5, and then the function says multiply it by 7. And so the output will be, I want to color code my output. The output will be 7 times x plus 5. And the insight here is that since this function in our box, since f of x equals 7x is a linear function, this means that the following. So since f of x equals 7x is linear, we know that f of x plus 5 equals f of x plus f of 5. So we can apply the 7 to the x and the 5 separately, giving us our result, 7x plus 35. Okay. And how do I know that this function f of x equals 7x is linear? Well, you can think about the graph. You know, the graph looks like this. F of x equals 7x, and we know that this is a linear function. Okay, well, great. So I'd be thinking if I were you, man, this seems like a slightly harder way to do this problem that I already knew the answer to. So this next slide will show the power of this. We're making some connections between different types of operations. So let's say that we had a plus b squared. Okay, does this equal a squared plus b squared? That's a really common mistake, right? That's not what it equals, but that's a really common mistake. Let's see why that's wrong. Okay, so for our input, we're putting in a plus b again. Okay, so I'm putting in a plus b, and what I'm doing is I'm squaring it. So f of x equals x squared. All right, and the output, when I square my input, I get a plus b squared. That's what's happening. But is this function linear? F of x equals x squared? No, it sure isn't. That looks something like this. Okay? That's not a linear function. And so, as a result, since f of x is not linear, I can't just apply the function to both additive inputs separately. I can't just say that it's f of a plus f of b. All right? Instead, I would need to FOIL this out, right? Really, it's the case that a plus b squared is a squared plus 2ab plus b squared. We'd have to FOIL. Okay? And we can remember that it's not just going to be a squared plus b squared because the function f of x equals x squared is not linear. Let's see another example. All right? And maybe you'll start to see why this can be kind of a cool and useful concept. All right, so what are we putting in and what are we getting out this time? So f of x, in this case, think, what's f of x in this case? It's the thing we're doing to our input. We're going to be taking the square root. And what we're putting in, as before, is a plus b. We're going to put in a plus b. We're going to take the square root of it. So of course we get out just the square root of a plus b. And now ask yourself, is this equal to square root a plus square root b? Well, is this square root function linear? And the answer is no. The square root function looks like this. All right, it's not a straight line. And since this function, the square root function, is not a straight line, right, that means that the square root of a plus b does not equal square root of a plus square root of b. Okay, because the square root function is not linear. Pretty cool. And maybe we're starting to see why this is kind of interesting and kind of powerful way to look at this. So now let's talk about trig functions. So let's say we're putting in a plus b, and we're applying the trig function sine of x. We're going to take the sine of a plus b. And then when we get out sine of a plus sine of b, or whoops, sine of a plus b, I mean. And the question is, does this equal sine of a plus sine of b? To answer that, all I need to know is the sine function linear? Okay, sine is not linear. All right, so that means that sine of a plus b does not equal sine of a plus sine of b. This is another pretty common mistake that students make when they're dealing with trigonometric functions and addition of angles. We can't just split it up over a and b because sine is not a linear function. Okay, fantastic. The same would be true for both cosine and tangent. Those aren't linear either. And so we can't split up the function over additive inputs for sine, cosine, or tangent. Let's look at this one, fractions. So a plus b divided by 3. Let's look at that. What's f of x in this case? What's the operation that we're performing, and what are the inputs? Well, the inputs are still a plus b. We're dividing them by 3. So f of x equals 1/3 x, or equivalently x divided by 3. The inputs, like with all of these, it's a plus b. And the outputs, we're getting a plus b all divided by 3. Yes, quadratic equations are also functions. Good question. And we can look at some examples of that a bit later if you would like. We saw a bit of that with the quadratic, or like with the squaring. Is the trig function in pre-cal or calculus? Yes, it's in both. Yes, you'll see trig functions for the first time typically in your pre-calculus class, and then they'll come back and still be around when you take calculus. Yeah, good question. But you'll see those. Sometimes the teacher will sneak them in during one of your algebra classes, but you'll really work with them in pre-calc. Yep. Good question. So in this case, the function is just that we're dividing by 3. So it's 1/3 x. So what does the function of 1/3 x looks like? Well, that is, I meant to draw it through the origin. Whoops, I missed a little bit. But this is roughly what f of x equals 1/3 x would look like. It is linear. And so that means that we can split up the division over the a and the b. This is a really common mistake students make when working with fractions, because students will try to memorize what you're allowed to do with fractions like this, but perhaps it helps you remember if you're able to tie it in to this broader concept about linearity. Okay, since dividing by 3 is linear, that means I'm allowed to split up the 1/3 over the a and the b, like I've shown here. Okay, and that's just what it says below too. This is linear, so we are allowed to split things up. What about this other similar looking operation with fractions? In this case, it's 3 divided by our input. That's the function that we're working with. So we're putting in a plus b, and we're saying 3 divided by that. 3 divided by the thing that we're plugging in. Okay, and what that spits out is 3 divided by a plus b. And the question is, are we allowed to split this up as 3 over a plus 3 over b? Okay, and to answer that, we should think, is 3 over x linear? What does the function f of x equals 3 over x look like? Is it a straight line? No, it's like the function 1 over x, which gives you a hyperbola, technically, but regardless, it's not a straight line. 3 over x, this is not linear. Okay, so that means that 3 over a plus b does not equal 3 over a plus 3 over b. Can't do that. Okay, that's also a really common mistake that even advanced students make when they're working with fractions. Okay, because it's so easy to forget. Are you allowed to split it up? Are you not? No, you're not. And the way you can remember is that 1 over x is not a linear function, so you're not allowed to split it up like this. Cool. We'll just do 2 more quick examples. So exponents, 10 to the a plus b. We're putting in a plus b. We're going to raise it to a power. We're going to raise 10 to the a plus b. So we're saying 10 to the x is our function. Okay. And then the output is 10 to the thing that we put in, a plus b. Is 10 to the x a linear function? Well, what does 10 to the x look like? Something like this. Okay, not linear. So 10 to the a plus b does not equal 10 to the a plus 10 to the b. All right, can't do it because this is not a linear function. Hey, by the way, if you saw our previous video about exponent rules, maybe you remember that 10 to the a plus b, what does it actually equal? Think for a sec. 10 to the a plus b is 10 to the a times 10 to the b. And you can see our previous video about exponent rules for more about that and other related manipulations with exponents and other exponent rules. What about logarithms? Don't worry if you don't know what logarithms are. We'll actually cover these in a future video. And these are also something that you'll typically be introduced to and work more with in pre-calculus. Sometimes you'll see them a little sooner. But for those of you who are familiar, the idea here is that we're putting in a plus b. The function we're applying to it is log. We're taking the log of x. And then, find my colors. There we go. Then the output is going to be log of a plus b. And the question is the log function linear? Turns out that no, the log function looks something like this. And so as a result, log of a plus b does not equal, right, because this is not linear, does not equal log of a plus log of b. This is a pretty common mistake that students make, thinking log of a plus b is log of a plus log of b. So we're tying all of these different mistakes together if you can understand this concept of, is the function linear? Log is not linear, so you cannot do this. Okay, because its graph is curved. All right. So I hope that's helpful. Take a couple of minutes again to go through these and mark each of the following true or false. Okay, comparing to your answers before and seeing what you may have learned during the presentation. I'll give you just like 20 seconds to look over it, and then I'll just mark each answer and talk through them very quickly together. And remember, feel free to type any questions you have into the chat. I love questions. I'm always happy to answer as many questions as you have. Okay, we'll start going through these. It's okay if you hadn't finished double checking everything yet. The first one is true. We saw that f of x equals 3x is a linear function, and so this first one is true. this second one is false because I'll mark this f of x equals 3x. The second one is false because we're relying on f of x equals 7 over x, which is not linear. This third one, I see a question. So for fractions 1, you have written f of a plus b is not equal to f of a plus f of b. Can you please explain if it is linear? Shouldn't it be equal? Yeah, great. Thank you. That's a really good question. Hopefully what I'm about to say will answer the question, and if not, let me know. So for fractions 1, so 7 divided by, or actually here, I forget which one was fractions 1 and 2, so let me go back to make sure I know which one you're talking about. Fractions 1 was when it's a plus b in the numerator. Okay, good. Great. So the question was about this guy. Okay, so the question was, is it true that f of a plus b, so for this kind, when we have two things that we're adding in the numerator of a fraction, that is on the top of a fraction, when we're adding two things on the top, then it is the case that f of a plus b is f of a plus f of b. That is true for number 3 on this list. And that's because the function that we're working with is x over 7. That's the thing that's the function f that we're plugging different values into on the top, additive values. Number 2, however, is false. And this is because the function we're dealing with is like something over, or 7 over x, 7 over something. And this is not linear. Okay, because 1 over x is not a linear function. So f of a plus b in this case does not equal f of a plus f of b, because in this case, 1 over x is not linear, or 7 over x still not linear. Okay, so hopefully that helped and made sense. Number 4 is false because f of x equals x squared is not linear. Okay, number 5 is also false because f of x equals square root of x is not linear. Okay, and then, good, I see a question. Does the rule of sine also apply to cosine and tangent? Yes, absolutely. Because in all 3 of these cases, all 3 of these are false. And that's because none of these trig functions are linear. Okay, so I'll say f of x equals sine of x is not linear. And then ditto for cosine of x and tan of x. Okay, none of those is linear. And so in none of those cases are we allowed to just split up the function over the 2 arguments. All right, same thing for logs, same thing for exponents. I included these 2 calculus ones because it turns out that, or here, let me finish labeling these. So like we saw in the presentation, logs and exponents are also not linear. So these don't work either. For 11 and 12, though, it turns out, and it's okay, I know a lot of you probably haven't seen calculus yet. I just wanted to give some additional examples of linear functions. Again, don't worry about this if you haven't seen them, but it turns out that both of these are true as well. Differentiation and integration are also examples of linear functions. All right. So good. I hope that this was helpful, and I hope that it helps tie together some different types of math mistakes. At the very least, this was some practice with different types of fractions and how you're able to simplify them, and simplifying things like squares and square roots. And hopefully this helps sort of explain and make it easier to remember where some of these rules come from. Since somebody asked about it, I wasn't sure if I would mention this slide, but linearity is also an important concept as you continue deeper into mathematics and science. So like for the SAT or ACT, the stuff we were talking about today with remembering some of those rules is helpful. But also if you continue further into some of these fields, like if you want to study, say, robotics, then linear algebra, which is a branch of mathematics concerning these types of linear equations and linear maps that we were talking about today, and their representations through vectors and matrices, can be useful, say, in robotics for describing rigid body dynamics, or can be useful for, say, computer vision or graphics in computer games for describing the relationship between a three-dimensional scene and its two-dimensional plane representation. So some of the things we were talking about today are useful in some of those more advanced fields. Oh, good question. Would questions like 11 and 12 be on the SAT? No, you won't see any calculus on the SAT. You will not. So yeah, absolutely. You'll see some of this stuff in more advanced places. So if you do continue on, it'll be useful. Let's leave it there. Do you guys have any further questions? Anything else you wanted to ask me about before we wrap it up for the day? Oh, yeah. So these are just some more examples of places where linear functions can be useful. I don't want to make this seem too scary, since I just want the things that we talked about to make sense. But these are just some future places where linearity is useful. But I will answer your question, which quantum mechanics is the physics of very small things. So like atoms and molecules and how they interact with each other. And this is very different from how bigger objects in everyday life interact with each other. If you want a good example of this, look up on YouTube, like the double slit experiment, and you can find some really cool stuff. That's a good way to be introduced to quantum mechanics. It's a simple experiment with light going through two holes and how it interacts with the screen behind it. The mathematics of quantum mechanics relies heavily on linearity, like we were talking about today. Like one cool example of this is quantum computers. Each operation can be described as a mathematical function. And it's the fact that these functions are linear, which allows for something called quantum error correction, which is what makes these computers possible to build in theory. Although that's still a very difficult challenge that scientists are still working on. But yeah, again, just like that's like a place in like real life, so to speak, where these ideas become pretty useful. But that's beyond certainly what you would see in high school. That's more of a thing you might study in college or graduate school. Yeah, sure thing. So I see, yeah, another question. Can I elaborate on number 11 or number 12? Yeah, sure. So this might get a little bit beyond like high school type stuff, which like most of the presentation was focused on. So I don't want to get too deep into this. You could always, shoot us an email if you want to sort of like, dive into more depth on some of these more advanced topics. But just to elaborate momentarily on 11 and 12. So what these are saying is if you apply the derivative function to two different functions, say f and g, this is the same as applying the derivative to f and g separately. And then similarly for number 12, if you take the integral of two functions, this is the same as integrating those two functions separately and then adding the results together. So for example, this would allow us to do something like this. Let's say that I was trying to take the integral of, say, x squared plus 7. Then this rule tells me that I'm allowed to split up the integral and evaluate it separately. So I could first integrate x squared and get x cubed over 3, evaluated at whatever my bounds are. And then I could do the same and integrate 7 to get 7x, evaluated at my two bounds. So again, I don't want to go into too much detail about this, just another example of where you'll see this kind of thing in the future. All right, thanks everybody for joining me. We will have more sessions like this every Monday, alternating between math and ELA type topics. Thanks for joining us, and I hope to see some more of you again in the future. Enjoy the rest of your afternoon. Thank you.